All right, welcome back, students. Today we are going to move on to another topic. Um, so far, we have looked at the DC-DC conversion. You're familiar also with um, AC to DC. Now, in today's class, we are going to look at DC to AC conversion. And we normally use what we call inverters for that. So I'll just go through the basics with you to start, right? So these are DC to AC converters, right? So we can use it to generate DC supply, yes, because it moves from DC to AC. Of course, you know, to move back from AC to DC with your rectifiers, right? So we can use it as a source of our DC supply. So also, what it does, we can have single phase as well as three phase supply. All of this from just a single DC source, right? And we'll be looking at the three in a little while, right? So how we use a single DC source to produce a single phase AC and three phase AC, right? So I'll be looking at that shortly. All right, now we start with the basic building block of the inverter, right? Let's call it a leg. It looked like that, right? So that's the inverter leg. As I can see here, we have our DC input and the output here. This should be our AC. Typical components here. You have your power MOSFET, T1, T2, and you have your power diodes D1 and D2, right? Very basic. Going to look now. Of course, I'm going to ask you a question. Of course, these, you know by now, these transistors, they are there as switches. Can we switch on T1 and T2 at the same time?
Also, we'll have a short circuit across the source.
All right, very good, right? We don't want to switch on T1 and T2 at the same time because we're going to have a short circuit across the source. Very good. All right, I should also mention to you that it is pulse width modulation that we're going to be using to switch the T1 and T2. Right, and we say when we have that kind of switching where T1 switch on but not T2, then T2 switch on and not T1, right? We say complementary switching. Right, we can use microcontrollers to enable this kind of behavior. All right, so we never have T1 and T2 turn on together, and of course you just give me the reason. Right. All right. So the output voltage, right, is just a fraction of the DC, right, and it's going to be the ratio of T on to the due to the period, right, multiplied by the DC, right, VDC here. That's all the output is, right? So in other words, this part here is your duty cycle. That's your duty cycle, and here we're going to. I'm just going to quickly review the whole concept of the pulse width modulation. Right, so we can have our carrier, right? That's the actual signal that we're going to be applying to the sinusoidal wave, as you can see. And a sawtooth waveform, right? That is what you use to generate the pulse width modulation, right? So where we actually use this, is to switch the MOSFET, right? So that's what we're using the pulse-width modulation for, switch them on and off. So we then can connect that to some comparator, right? So if we look at it, so if we have the modulating signal going below the carrier waveform, all right? So let's mark off our switching points. These are the points that you'll have switching taking place. So comparator, we look at the two voltages, the carrier and the modulating waveform. Carrier is below in this region, as I can see, it goes to 0. Output is 0. Output of the comparator 0. Right, the carrier now rises above the modulated, the carrier waveform, as I can see, carrier above. So it goes high. In this region, carrier is below the carrier waveform, so it goes to low. Right, and it goes on and on, as I can see. Our switching frequency is just 1 over the period, right? And we say switching period, SW here. So our duty cycle, can get it from here, is the ratio of T on to the period, right? So, and here is the switching period here, right? So just a quick review. All right, so let's now move to the whole operation of this device. We're going to connect a load to it, right? And here I'm connecting an inductive load. Of course, we have a resistor in it. Practical, that's what we're going to use the inverter for. We're going to connect primarily the inductive load. It could be a bulb, could be a motor, whatever. Right, so it's mostly inductive load that you'll be connecting here. So it's worthwhile studying this. So these diodes are freewheel diodes, by the way, and what they do, they ensure that you have unidirectional voltage and bidirectional current. All right, I'll be explaining that to you shortly. All right, so as I can see here, if we have T1 on, right, when we have T1 on, you're going to have current flowing like this. T1 on, current will flow, take that path. T2 off, right? So T1 on, remember that both of them, we don't turn them on at the same time. Right, so T1 is on, we'll have current flowing from the source. It goes through this T1 transistor. It will not go through this diode, right? It's reverse bias, so it will take this path, right? So that's the path it will take when T1 is on, right? When we have T2 on, right, what we're going to have, which will be 0 volts, right? Because it's not a switch. When the switch turn on, the voltage of across the switch, what we discussed earlier on, is going to be 0 volts. So that's what is going to happen. So when it's on, basically the energy that is stored in the inductor is now going to be released, right? So that is what you will see happening here, right? So you have the current now flowing basically in the same direction as when T1 was on, right? So that's what is happening here. Very, very simple. All right, now you notice T1 was on, what was happening? Now, if we have T2, we can have energy being absorbed, energy absorbed by the source, right? Look at this. If we have T T2 and T1 off, right? We can have energy being released to the source, right? Of course, when T2 turns on, the voltage drop is going to be zero across on this switch, right? So we can have two current going in either from the source in one case or from the load back to the source, right? So depending on the switching. We can look at what we call the IV graph. Based on what you would have seen here earlier on, we can have these two quadrants, right? You would have seen where the when the voltage is positive, we can have positive current, voltage positive, we have a negative current. So these are the two quadrants. So these are the two scenarios that we had. So we can also now look at the average output voltage of this device. I showed you earlier on that this is just the ratio of T on to the switching period times the input voltage, right? In other words, the input voltage multiplied by the duty cycle, right? Or we'll call it modulation index. Every while you see why I'm referring to it as modulation index, right? So let us say M, modulation index, T1, that's T on ratio of T on to the period, right? We're going to now substitute back this into our expression for our average output voltage, right? So T on to T, right? That's just M. So so our output voltage is equal to the modulation index or our duty cycle multiplied by our input voltage. And of course, you know that the modulation index is going to be between 0 and 1. All right, so just some points to note as it relates to the switching frequency, right? The switching frequency, the first point here is that the switching frequency of the pulse width modulated signal, right? We usually take it as the highest, as high as possible, right? So as to reduce the ripple in our load, right? And this maximum that we'll select is going to be limited by the losses and the ability to manage the losses in the device, right? So for low power circuits, you can have switching going as high as 1 megahertz, and for high power, and by high power I mean greater than 500 kilowatts, right? You can use frequencies of about 1 kilohertz or less. All right, so this now takes us to what we call the single phase H bridge, right? That single phase AC that I mentioned earlier on are the three phase. So we're going to start with the single phase H bridge, right? So it's like if you look at it, look at the configuration. You have the two legs. We join the two legs in parallel, right? So that's where. So this is one leg. This is the next leg on this side. So it's like between we have our load. So it's like what we have we have an H, right? Looks like an H, right? So we refer to this as our single phase H bridge. All right. It's very simple. It looks a little complicated, but very, very, very simple, right? You would know to draw just one leg. So put another leg on the other side, and between we have our inductive load here. All right, so we have our input voltage here. So what we get out, we have our output voltage right here. And on this side, we also have our output voltage here. So VAO, that's the output voltage on this side of the load, and VBO, that's the output voltage on this side of the load from the next leg. So of course, what's going to be the potential difference across your load here? Just a difference in potential, right? VAO and VBO, right? That's clearly what this load is going to see. All right, let's look at it. Let's bring this up. So earlier on, you'd have seen what the output voltage is, right? You remember we looked at it a while ago when we studied this, right? And we developed this, right? So the output voltage, as you can see here, for just one leg of the bridge, is just the modulation index times the input voltage, right? Very simple. So if we have two legs, right, we can write the formula there, right? So leg one, let's call it leg one, that output voltage is going to be some modulation index times the input voltage from that bridge. And the leg two, let's say this one is leg two, VB output is going to be some modulation index, let's call it MB times the input voltage, right? Of course, the input voltage is common to the two, they're in parallel. Right? I know somebody wondering where that is coming from. They're in parallel, so they're seeing the same input voltage. All right, so we're now going to ask ourselves, what's the average output voltage? Just like we did earlier on with just one leg, right? One leg, it was easy. See that it was just a fraction of that input voltage. But now we have the two in parallel. So what is going to be equal to? Very simple, right? We just take the difference, right? The potential difference. If we know what VAO, that's the output voltage of, let's call it leg one, VBO, the output voltage of leg two, right? What's the potential difference? We just take the difference. Of course, we have the two voltages here. Take the difference in voltage and we end up with our first equation for our single phase H bridge. All right, now remember these are, or what we refer to as our modulation index, right? So these are going to vary sinusoidally, right? So if they are going to vary sinusoidally, we can just write the expression like this. Hold on, right? This thing not coming. Okay, all right, I don't know. Right, comes up. So it's giving you trouble there. Good. All right, so rewriting it, since we know that MA and MB must be sinusoidal, we can rewrite it like this. If you notice, one of them plus and one minus. If we add the two, the sinusoidal component is gone, and MA MB is just equal to 1, right? So it's just be MA minus MB, right? So it's just to show you how this maybe this concept is developed, right? So we want MA and MB to be sinusoidal. So we do it like this, right? So half plus M, that's modulation index, sine omega t. And the half minus M, that's modulation index, sine omega t. So we have three equations here, 1, 2, and 3. I just want to move. All right, good. Move on. So we can put those together, those three equations, right? Okay, just substitute, that's all we're doing here. right? We have MA, we're going to put it in this equation. MB, we're going to put it in this equation. And when the dust is settled, right, it comes to this, right? As you can see here, we just have 2M input voltage times sine omega t. And of course, now what's going to happen? Your modulation index is going to now be between the half, because we split this. Hold on, sorry, let me go back. Because of the half here, right? Refer to this as modulation depth. It's going to be between 0 and a half, right? So we can now use this part, right? Remember, we can control this, right? The modulating index, right? So we can remember this is the amplitude, right? So basically, by manipulating M, that's the modulation index, we will be able to manipulate the output voltage. That's the magnitude of your output voltage. And we can also manipulate the frequency, right, by adjusting omega t. So you can design your inverter, right? You want a DC, you know what your DC input is. You can set up your modulation index so that you can get, you want 50 volts, you want 60 volts. Of course, your modulation index you'll use to control that. And to change the frequency, you just use omega t, right? That's what you manipulate here. All right, so we say that our DC offset, right? So these are the half, right? They disappear when the dust is settled, right? So important to note here, they are in phase. We say co-phase, right? So we don't have them in the output voltage, right? So basically, we're able to control our magnitude and frequency. And this H bridge, we can basically operate in all the quadrants. All right, just to look at the generation of the pulse width waveform. So we will have our sawtooth waveform, and that's the carrier, and M1 and M2. These are going to be what we use to modulate the sawtooth waveform. All right, so again, it's very simple. You look for your switching points. Let me do them one at a time. So we look at the first leg, then the second leg, right? Identify the switching points on your first leg, right? So that's a switching point, that's a switching point, that's another switching point. And remember, so if it is the modulating signal is, well, I'm starting from the second one. Sorry about that, but let me go to the first one. Right, so M1, right, so that's a switching point. M2, that's a switching point. M1, switching point. So we'll go to M1. Right, so it is above the carrier. So if you come down, see it starts high. But if you look between here, it goes below the carrier, so it goes low, right? All of this, the two signals, they are going into a comparator, right? So that this wave can be realized, right? If we look at M2, right, we have the modulating signal is above, right? So what we're going to have is going to start high, then between this switching point, and this switching point, we have it below the carrier waveform, so it goes low, right? So that is what you have happening, and it goes on and on. You can work it out later on, right? So leg 1 and leg 2, this is going to be what you have at the output. Now, what is the load seeing? The load is going to see the resultant of these two voltages, right? So the resultant is given here at the bottom, right? When you add the two, it basically is a superposition of the two waveforms, right? So that's the resultant. All right, so it must be mentioned here that you'll have some harmonics in the output, right? Let me now move to the three-phase inverter. Again, we're using the same principle. You know, the single phase, you can easily go to the three phase. We just connect another leg, right? Remember, we had one leg, two leg, we get the H bridge, right? Then we connect another leg, right? And we now have the three-phase inverter, right? So what we have here is our three-phase inverter, right? And again, we're going to do the same thing. This is our input voltage, VDC, and our output. This is the first leg, VAO, and the second leg, VBO, and the third leg, VCO, right? Of course, the input voltage to the three is going to be the same because we connect them in parallel. Right, so we can apply the same reasoning as we have been doing earlier on. So what is it? VAO, what's the output voltage of the first leg? It's just going to be, let's say MA, whatever that modulation index is, and the input voltage. What is the output voltage of the second leg, right? That's VBO. Whatever the modulation index is set it to be, multiplied by the input voltage. What's the output voltage of the third leg, right? Let's say VCO is going to be whatever that modulation index is that you set it to be times the input voltage. And of course, if you look at this, you have the load between three-phase load, right? So you can have let's say A, B, and then V, B, C, and then V, C, A, right? So that's what we have here, these lines, right? So V, A, B, V, B, C, V, C, A, right? And of course, you can now get these three expressions here. You know what VA is and what VC is, sorry, VB. So VA minus VB will give you this expression, first expression here. Second one, VBC is going to be VB minus VC. You get the second one here. VCA is going to be VC minus VA, and you get your third expression here. Now, for the modulation index, this is how you're going to set them up now. Because we want a phase shift. Remember, with our three-phase system, we have the magnitude of our voltage here. Let's say we want it to be the same. However, we have a phase difference, right? We want to realize a phase difference of 120 degrees apart. So this is how we set up the modulation index, right? So minus 2/3 pi plus 2/3 pi and 0, right? So that's our phase difference here. So when we insert or substitute or MA, substitute or MB, and so on in these three expressions, and the dust is settled, we will arrive at these three expressions here, right? So VAB, VC, VCA. Right? So we have our three-phase output voltage here. We look at the six-step operation. I say six-step because I can see here we're going to switch these switches. We have six of them, right? Six switches. We're going to be switching them sequentially. Of course, you can do that using microcontroller, right? So as to get accurate switching, right? Just to mention what you get out, I'm going to be looking some square wave. That's why you're getting also the VAO, VVO, VCO, right? It will look like that, and you can see they have the phase shift there, right? Of course, if we do the Fourier analysis on it, for VAO, this is what we end up with, and we can also do it for line to line. We go line to line. This is what the waveforms will look like, as you can see displayed on the left hand side, right? Of course, just like with the single phase, you had harmonics being introduced. With the three phase, you also have harmonics being introduced. And of course, this will cause loss. This will add to further losses, right? So I'll just finish this topic on inverters with some applications, right? Of course, PV application I'll look at, right? So, with a small home recreational use, you just have a single panel, you have a charge controller here, your battery, right? It prevents your overcharging of your battery here, right? And then you can get your source here, your DC supply at this point, right? So again, if we want to have this, could be for home recreational use, industrial use, set up a bigger system, right? Grab more battery for storage, for electricity, we have a charge controller, and of course we can top off our DC supply here. Alright, so where's the inverter? Alright, so we can put, we want AC, alright, so there we can put our inverter, alright, so we can supply DC and AC loads here, right, by just putting in an inverter at this point, convert from your DC to AC, right? Of course, you could have what we call, we could do away with the storage, right? And just have our panels feeding that DC source straight to our inverter and convert to our AC, right? And of course, we can then top off to our electric grid. Could have a hybrid system as well, right? Sun and wind, right? So could have it set up, right? You have a battery charge controller here, so you top off your DC supply, your wind and your wind turbine here. Convert your DC to AC here, so all of that could take place there. what I'm showing you here, um, just just to point out to you here that um, some of the energy from the plant is used internally to probably you need lighting for the office. You may have offices on the plant. You need to power up your devices that you're using in the plant. Right, normal equipment that you'll find in the offices and also to run the equipment. So sometimes what is reported as the output of the plant may seem to be less, and it's because this is taking out the internal consumption. I think that's it. That's it, right? So thank you very much for listening. Keep safe. This is where we will end this lesson as well as